Hello, my name is Isabella Rangos, and this is Lab 2, Lines of Charge. In this experiment, I explored the behavior of charged tapes I made when they interact with each other. Using measurements of the tapes, I was then able to determine the gravitational and electric force acting on the top tape. I used this calculated electric force to estimate the amount of charge on each tape, which is necessary to make the top tape float above the bottom tape. I then created a computational model illustrating the equal distribution of charge over the entire tape and modeling each tape as a line. In this lab experiment, I used two main fundamental physical principles as the foundation for my experiment, calculations, and computational model. These were the gravitational force and the electric force. I made several observations before conducting my experiment that allowed me to calculate specific results. I measured the length of the tape and used it to find the mass of the tape, and then measured the distance between the tapes when the top tape began to float. These values allowed me to calculate the magnitude of the gravitational force and the electric force on the top tape. After conducting my experiment, I began to create my computational model. Here's the function I created in Lab 0, which I then used in this lab to calculate the electrical field. In these lines of code for the top tape and bottom tape definitions, I edited the vector and axis values to reflect the distance I measured when the top tape floated above the bottom tape. I also created an estimate for the number of charges in this model, selecting 9 as my value. I then edited the scales for the arrows that would illustrate the electric force acting on the top tape as a whole and on the individual charges that were selected to act as the makeup for the line model. I then wrote lines of code to calculate the electric field at the top tape and the electric force on the top tape by the bottom tape. Here is the result of my computational model, with the magnitude of the gravitational and electric force equaling each other in the output. In the model itself, the green arrows represent the net electric field of the top tape, evenly distributed across each individual charge. The white arrow represents the net electric force on the top tape by the bottom tape, and the yellow arrow represents the gravitational force. The charge estimate for this model was found to be 4.0454 times 10 to the negative 9 coulombs. In this experiment, the only assumption made is that the U-tapes have the same amount of charge that was evenly distributed across the entire tape. I did not have to ignore air resistance because the tape was not moving at its peak position when I measured the distance between the tapes. Therefore, at this equilibrium point with no motion, air resistance is not a factor. What if each tape was modeled as a single point charge instead? As seen in Lab 1, here are the computational model results showing the different forms of representing the top tape and the bottom tape. The estimated charge of the tape when it is modeled as a single point charge is almost twice as much as when the tape is modeled as a line charge, separated into 9 different units. Why do these estimates differ? The line charge model uses the length of the tape and an estimated number of charges in the calculation of the electric field and force. Therefore, the charge of the tape that allows the gravitational and electric force to be equal will vary based on the tape's length and number of charges, and will not be equal to the simpler calculations when we assume that the tape is a single point charge. In conclusion, this lab experiment allowed me to model the tape as a line rather than a point charge. The resulting charge estimate is much more accurate than the point charge model because we don't have to assume that the entire tape's charge distribution is at a single point, instead of how it would be in reality when it is distributed across the length of the tape.